is the detection image in the optical band. Here is the galaxy at different time slots. So if you subtract this image, this image, you can find the transient point source here. And this is the gravitational wave source event. Because this event is closing now, 40 megaparsec. So a bunch of telescopes perform the spectroscopy. And right-hand side here is a summary of the spectroscopy from UV, optical, and IR1. And color means a day after the emergence. Within 1.5 days, say a purple or red color, blue color, the photon is emitted in the UV band, and the shape of the spectrum is a quasi black body, which means a quasi thermal radiation. Then this emission shift to the IR direction.
Sorry, can you speak from here?
Where?
From here.
Yeah. Okay.
Yes, perfect.
Okay, within 1 week. So this emission is classified into the short duration UV blue component and long duration IR red component, at least. So this is a very important message as well. For the GRD 700870A, the film GBM and integral observed gamma ray photon from 1.7 second after the merger. Here is a spectrogram and chart. Here is a merger time, and 3 panels is gamma ray observatory data. And you can see that the gamma ray is detected just after the mergers. Because the T19 is about 2 seconds, this gamma ray burst is classified into the short gamma ray burst. However, the isotropic equivalent energy in the gamma ray burst is about 5 times 10 to 46 cells, which is very smaller than the canonical one. Canonical short. This was one basically. And final one is a long term, say about 160 days observation in radio and X-ray. Here is this spectrum frequency versus flux at the radio, optical, and X-ray band at 9 days, at 15 days, 108 days, and 160 days. This spectrum is nicely fitted by the standard synchrotron afterglow model because the matter is ejected from the system. Then this matter interacts with interstellar media, then the shock is generated. At the shock, the electron is accelerated and random magnetic field is produced. Then so you have an electron and magnetic field that synchro radiation outputs. This is a standard picture of the synchrotron radiation afterglow, and this model nicely fit the observation result. But at this moment, we didn't know what causes what is the mechanism of the mass ejection or matter ejection at this point. However, after almost 1 year after 1 year's observation in radio band, this result was disappeared. Here is a so-called superluminal motion of gravitational wave sources in the radio band. Here is just after the merger, and here is almost 1 year after the merger. You can see the motion of the emission regions. Because if the source moves with the almost speed of the light, it causes apparent velocity which is greater than speed of light. It doesn't mean that the break of the causality. It is a superluminal motion of the source image. You can estimate the motion of this relativistic. You can measure the relativistic motion of this source image. In addition, the light curve shows that sharp declines at 170 days after the merger, which suggests that a relativistic motion as well. So these observations strongly suggest that the relativistic jet was launched from this bidirectional star observation, and this also is compatible with the short gamma ray burst observation. Okay, let's move on to the theoretical point of topic. Today I'm going to talk about various topics on this phase diagram. Here is a schematic diagram of the binding nucleoside evolution from spiral, mergers, and aftermath. And after the merger, you have several possibilities for the evolution process. But in GW70OH17, it is considered that the hypermassive neutron star is tangentially after its form, tangentially formed after the merger, and it collapses the black hole. Why? The logic is very simple. The remnant rotational energy of the hypermassive neutron star is almost 10 to 43 L's with a typical the binary parameter, typical remnant parameter. And suppose that the remnant survives long enough, the dipole radiation extracted this rotational energy on the time scale of the spin down time scale, 200 seconds or something like that, with by assuming the magnitude strength for dipole magnitude strength. So this means that if the hypermassive neutron star survives longer than 200 seconds, the energy of 10 to the 53 L's is injected in the ejector, and ejector could shine. However, the electromagnetic observation suggests that the energy in the electromagnetic emission is about 10 to the 51 L's, which is incompatible with this number. So that means the hypermassive neutron star collapses this black hole shorter than this time scale. Then the black hole and accretion torus is finally formed, and this could launch a relativistic death. But theoretically, it wasn't clear. It is still unclear. So let me explain about the optical infrared emission from binary neutron merger. Because during the merger process, a significant amount of the neutron at the edge is ejected. Then inside the ejector, the neutron is captured by the seed nuclei. This is called by the R process or rapid process because the time scale is shorter. The time scale of the neutron capture process is shorter than the beta time scale. So once the nucleosynthesis happens, these heavy elements radioactively decay. So this radioactively decay gives you the heating source. In addition to that, the R process element provides opacity. In particular, the lanthanide element provides opacity. The typical opacity is 10 square centimeter per grams. With this number, the peak time is given by equating the diffusion time scale and the dynamic time scale. In the early stage, because the density is so high, so the opacity for the photon is high. The photon cannot diffuse from the system. But this ejector is expand and the density becomes low and low. Then finally, the diffusion time equals to the dynamic time. At this stage, the photon emission becomes peak. So peak time scale is about 1 week for a typical binary neutron star merger. The parameter and the peak luminosity is something like this. This is the basic foundation of the optical infrared emission, or called kilonova or macronova emission. So here is a lanthanide. Okay, here is a mass fraction as a function of F atomic number of the R process nucleosynthesis. On this plot, you assume the so-called electron fluxion in the binary neutron star merger. Electron fluxion is an electron divided by the value of number. The right-hand side figure shows the opacity as a function of the wavelength with assuming the electron fluxion. So this figure shows that if the electron fluxion is greater than 2.5, the lanthanide elements are not produced, so the opacity becomes low. On the other hand, the electron fluxion is lower than 0.25. A bunch of the lanthanide are produced, and this then the opacity becomes high. Because the lanthanide has a bunch of the energy levels, the bound-bound transition produces high opacities. So neutrino reaction determines the electron fluxion of the ejector, so it is important to determine the emission process in macronova. So the question is, where does the neutron ejector come from, and what is the physical mechanism of the ejection mass ejection. The recent numerical relativity simulation revealed that mass ejection is caused by the two processes, dynamical rejector process and disk process. The dynamical rejector is driven by the tidal force as well as the shock heating at the generation at the colliding top of the two neutron star. This is one example of a simulation for the neutron radiation transfer in binary neutron star merger. For the left-hand side figure is electron fluxion. The right-hand side panel is the specific entropy at the meridian plane and orbital plane. In the orbital plane, you can see that the tidal component is ejected, and on the meridian plane, the shock component is ejected in the polar direction. This is the basic picture of the dynamic ejection. After that, the second component is a disk ejector. This disk ejector is driven by the viscosity together with the neutron radiation. Viscosity, image instability produces a turbulent viscosity, and this viscosity causes angular momentum transfer and viscous heating. And with these three effects, I mean the viscous heating, angular momentum, and neutron absorption drives this ejector. So here is one example of a simulation in two-dimensional. I mean this is the orbital meridian plane of the major remnant, two-dimensional viscous radiation neutron radiation simulation. Here is a remnant machine neutron star, and you have a disk. Here is 300 kilometers, and here is more wire. Let's see. You can see that this window is driven from the disk surface, and this YE component of the disk ejector is high. So good. Okay. So far so okay. So, the physical, the dynamic rejector and disk wing component could be driven in the binary neutron star merger. The next question is what is the dependence of the dynamic rejector and the disk mass on the tidal deformability of the neutron or neutron star radius? The left-hand side figure shows the dynamic rejector mass as a function of the compactness, mass divided by the radius of the neutron star. Different color means a different division of state, and you can see that the dynamic rejector increases with the compactness. This is because the model with a small radius, neutron star radius, colliding motion of the binary neutron star with small neutron star radius becomes large because the velocity of the colliding motion becomes large, and then the shock heated component of the ejector increases as well. The central panel shows that disk mass, not ejector mass, dynamic ejector mass, disk mass as a function of the tidal deformability. This plot shows that the disk mass could correlate with the tidal deformability, something like this. Because a model with a small tidal deformability tends to collapse to a black hole in a short time scale, so it doesn't have enough time for the massive disk formation. So, okay. Then, David Radici and his collaborators suggest that with these numerical experiments and the tidal deformability should be greater than 400. Here is a summary of the plot. Here, the vertical axis is the ejector mass, disk mass plus the ejector mass as a function of the tidal deformability. And here is a requirement from the EM counterpart, and here is the bar, because this plot suggests that the tidal deformability should be greater than 400 this direction, right? But we are a bit skeptical about this result because they only adopted a very limited class of the equation of state. More specifically, all the equations of state they adopted is based on the relativistic mean field. So with Within this framework, the maximum of TOB star correlates with the tidal deformability. Why do we have to care about the maximum of TOB star? In general, a binary star with a large TOB maximum, large TOB maximum neutron star tend to have a long time scale after the merger because maximum mass is large, which means that it has a chance to form a massive disk because you have plenty of time for the angular momentum transport. If the maximum TOB star correlates with the tidal deformability, as the equation of state in the Lariche's paper, a model with small tidal deformability tend to be rejected from EM counter observation because such a model doesn't have enough time for angular momentum transport. As a result, the disk of the mass could be small. So we revisited this problem in numerical relativity simulations of binary neutron star merger with piecewise polytopic prescription, with which we can handle a correlation between the maximum TOB star and the tidal deformabilities. Here's a summary of our prescription. So with piecewise polytopic equation of state, pressure given as a function of rest mass density is divided in several segments. In each segment, you can tune the polytopic indices. Then you can handle the maximum mass and tidal deformability. Here is the MR relation of our model. More specifically, we prepared 3 TOB maximum TOB star, and tidal deformability is in the range from 200 to 600. Because we know the mass of the GW70 or 17, we perform the simulation for the equal mass system and unequal mass system. Before going to the details, so let me explain the 3 possibilities of a remnant. The fate of the remnant is classified into 3. The first one is binary neutron star collapses to a black hole immediately after the merger. We name this model as a no bounce model because there is no prominent bounce in the alpha, the minimum value of the Lux function. The second class is a short-lived case in which a transiently formed hypermassive neutron star collapses to a black hole within 20 milliseconds after the merger. The third one is a long-lived case in which hypermassive neutron star never collapses to a black hole in our simulation time, not physically, say within the 30 or 40 milliseconds or something like this. So in this case, we define the disk as a fluid element which has a mass density smaller than 10 to 13 grams per cubic centimeters. Anyway, so you have 3 possibilities of the remnants. Okay, let me show the result. And this messy plot, this messy plot shows the total amount of the ejector as a function of the binary tidal deformabilities. The color means the fate of the remnant machine star, purple for a no bounce model, green for a short lived, and blue for a long lived case. The field are open and field symbols mean that correspond to equal mass system and unequal mass system. Okay? Because there is no firm prediction about what fraction of the disk window mass, so we assume the efficiency this fraction from 0% to 100%. This is the meaning of the error bar. Again, 0% means that the disk wind is not ejected, and 100% means that all the disk is ejected as a disk wind. Okay? And here is an EM counter observation. Here is a body just bound, and this figure clearly shows a counter example for the plate by the luggage law. You can see that these models can explain the EM counter observation. Okay, let me see that it result in a different way. Here is a maximum mass versus binary tidal deformability, and small symbols is a model which fails to explain the EM counterpart, and large symbols means a model which success to explain the EM counterpart. Success or fail means above this line or below this line. And in this plot, we assume the 50% efficiency for this window ejection. For symmetric binary, the open symbols, there is no chance for the model with a tidal deformability smaller than 400. This is consistent with Radic's result. However, for asymmetric binary, in particular with a large maximum mass TOB star, the model with tidal deformability 250 still survives. So the message of this figure is that the joint analysis of the EM counterpart gravitational wave should be performed on the maximum mass and TOB star plane, and the accurate measurement of the mass ratio is also very important. So the open question is what is the realistic value of the fraction between the window mass and the disk mass? Because we didn't account the magnetic field or neutron radiation transfer in this simulation, we assume that this efficiency by hand. That's the meaning from 0% to 1%. But in reality, the MHD instability drives the turbulent, and then consequently the turbulent viscosity is produced. This viscosity is the main agent for the angular momentum transport and the viscous heating. So this determines this fraction. But we don't know how large the effective turbulent viscosity should be. Personally, I think only the high resolution image simulation could give this answer. But this is still a question. Okay, let's move on to another topic. So later on, I'm going to focus on the merger process in merger states, in particular the gravitational waves. The gravitational waves in the latent spiral merger phase contain the information of the neutron star matter, because the hypermassive neutron star depend on the equation of state you assume. So there are the post-merger signals is a very good target for the second or third generation of the gravitational wave detectors. So there are a bunch of the proposed universal relations between the frequency, post-merger gravitational frequency and tidal deformability or neutron star related quantities. However, the systematics were not well studied in the previous works, so we don't know how robust these universal relations are. We have simulated a bunch of the binary neutron star simulation. So let me introduce our circular gravitational wave from data bank. Here is a parameter space symmetric mass ratio versus tidal deformability. We have performed a simulation of binary neutron star. Different symbol means a different Chab mass. In each parameter grid point, we have performed a 6 grid resolution. And the highest resolution case is a 60 meter or something like that. And this is the highest resolution simulation to date. Not only outlook, but also in the world. So anyway, the gravitational wave cycle is a 30 or 32 cycles, and we release this gravitational wave from data on the website. So if you are interested in, or if you want to perform your independent analysis, please download the data from this URL. Anyway, with this gravitational wave data, we assess the universal relations. First one is a so-called F-peak lambda tilde relation. F-peak is a gravitational wave frequency at the peak time of the gravitational wave amplitude. And Retoro and Takami and the other guys propose a relation between the F-peak and lambda. We plot the F-peak and the lambda with our simulation data, and here is a Retoro and Takami relation. We found that this relation only for an equal mass binary, and not for unequal mass systems. For unequal mass binary case, you have a large systematic or large scatters. By the way, we place the error bar in each point by doing in-depth resolution study for a good resolution, and this is the meaning of the error bar. So why the universal relation doesn't hold for a symmetric binary? The left-hand side figure is the density contour on the orbital plane for a symmetric binary at the peak time. the gravitational wave amplitude becomes big. You can see that two neutron stars have already touched each other at the peak time, which means the separation between the two is short. This means that the peak frequency becomes high. On the other hand, for the asymmetric binary case, the less massive neutron star is tidally elongated. So when the two neutron stars get in touch, the separation between the two is large, which means that the peak frequency becomes low. This is why the universal relation is breakdown. Universal relation breaks down for asymmetric binary. So Ventura and Takami has partially pointed out this breakdown of the universal relation. Here is a peak frequency as a function of the tidal probability, and they are outlier. They are actually unequal mass binary. However, at that moment, so the number of samples is small, so there was not clear this outlier is important or not. But we conclude that the universal relation should depend on the symmetric mass ratio. So we propose an improved relation in which the coefficient depend on the symmetric mass ratios. With this relation, we find that the error bar scatter is less than 3%. However, the caveat is that even the improved relation could still suffer from the systematic because we didn't take into account the magnetic field on neutron star in this study. This is the one important fact. The second assessment is the F1 FP in the power spectrum density of the gravitational wave. Here is the power spectrum density as a function of frequency, and you can see that several prominent peaks. So in this talk, I'm going to focus only on this F1 peak and F2 peak, the most prominent and the second prominent peak, because the other one, personally, I think the other one are not relevant. And they propose that this F1 frequency is correlated with the tidal coupling constant, which is essentially same as the tidal probability. On the right-hand side figure is the PSD of our simulation data, and this vertical dash is their proposed relation, and different parameters are different, the resolution. And here is one equation of state, and here is an equal mass case. So you can see the prominent peak in F1 around here. However, if you decrease the mass symmetry, something like this, eta is a symmetric mass ratio. This means that you increase the asymmetry of the mass symmetry. The F1 peak disappears, something like this. Again, let me show again. Here is a symmetric binary, and asymmetric increases. Then the F1 peak disappears. So we found that this trend doesn't depend on the equation of state or binary mass. So we conclude that the F1 universal relation is not universal. The second one is F2 peak frequency, most prominent peak frequency here. And here is another model, our model, and you can see that the peak frequency, F2 peak frequency around here, but it slightly depends on the resolution. And if you change the mass symmetry, the position of the peak frequency slightly changes as well. So we conclude that a peak is affected by a finite difference error as well as the symmetric mass ratios. So here is Luciano and Takami's proposed relation for the F2 tidal deformity relation, and here is our Here's our simulation data, and we found that their relation produces 40% scatter. So why the universal relation don't hold. So Takami and Rettora proposed a mechanical toy model to explain the F1 and F2 cleavage. This is a schematic picture of the mechanical toy model. You have a rotating disk with orbital angular velocity omega, and you have two spheres which rotate with a disk. But these two spheres are connected with a spring, so it's free to oscillate. So you can see something like this. With this toy model, and given the angular momentum conservation, the smallest separation corresponds to the largest omega because of the smallest momentum inertia. This corresponds to the F3. I didn't mention the F3 at all, but anyway, this is the largest frequency. On the other hand, the largest separation gives the smallest omega. This corresponds to the F1, and F2 is average of the F1 and F3. So, according to this mechanical toy model, they simulated they evolved the system, and they plot the evolution of omega as a function of time. Please look at the top panel. And red curve is for the mechanical toy model, and here is omega 3 and omega 1, and here is omega 2. And blue curve is the simulation result, which means that this toy model will reproduce the omega 2 freakage. So they explain that this is a picture of the picture to produce the F1 and F2, F1 and F3. So let's go back to come back to the less mass density for the symmetric binary and asymmetric binary. Again, left-hand side of the figure shows the symmetric binary case. So you have two dense core even after the merger, and this dense core survives longer than the dynamic scale. On the other hand, for the asymmetric binary case, the less massive neutron star is tightly disrupted before the merger. The remnant core is one very dense core with a dense environment. So the mechanical toy model, which assumes the two sphere with a spring, could not describe the remnant for the asymmetric binary. This is why the universal relation don't hold in general. So we propose, improved relation for the F2, the tidal deformability, and the error becomes a little bit small. But the caveat is again that improved relation will still suffer from the system models. 20 minutes more. Okay. So far, we didn't take into account the turbulence, which is the main subject of this workshop, at all. So the question is, how does the turbulence change the story? The key ingredient is the effective turbulent viscosity, which is caused by the MHD instabilities. Before going to the details, so let me explain why the turbulence is connected to the viscosity. This is a very basic, but let me explain again. If you write down the equation of motion for a viscous fluid in the cylindrical coordinate, you come up with this term. This term derives the angular momentum transfer and the energy dissipation due to the viscosity. The next question is, what is the viscosity? And the answer is MHD turbulence. If you write the physical quantity small q, if you assume the physical quantity q is composed q average plus fluctuation term, and this variance denotes the time ensemble. The time ensemble q corresponds to the q average, and that for fluctuation vanishes. If you plug them into the equation of motion for the MHD magnetohydrodynamics, you come up with this term. This term is the sum of the Reynolds and Maxwell stress terms. If the correlation between the velocity fluctuation is positive, and this term works as this term works as a viscosity term. The thing is the same for a Maxwell Reynolds stress. This is why we need an MHD turbulence. Just want to skip this one. So what is the physical mechanism to produce electricity turbulence in binary neutral star major situation? The first one is the Kelvin-Helmholtz instability, and here is a basic schematic picture, basic fixture for Kelvin instability. In a very ideal case, all the mode becomes unstable, and the growth rate of the Kelvin-Helmholtz instability is proportional to the wave number, which means a small scale vortices has a large growth rate. In binary neutron star merger, this shear layer appears when the two-star neutron star comes into contact. Here is the density contour on the orbital plane just before the merger and just after the merger. And you can see that small vortices are produced. And these small vortices, they carve the magnetic field line, then magnetic field is exponentially amplified. This is a basic picture of the magnetic field amplification in binary neutron star mergers. And I did a large-scale simulation, and here is a magnetic field energy as a function of time. Here is a merger, and different color means a different grid resolution. Here is the lowest resolution case, and here is the largest resolution case. And the factor is about 10 for the grid resolution. And you can see that the energy for highest resolution case, the energy of the magnetic field is amplified by the factor of 10 to 6 at least, which means that the average magnetic field strength is amplified by the factor of 10 to 3 in a very short time scale, within 4 milliseconds time scale, something like that. In reality, however, the growth rate growth rate doesn't converge with respect to the grid resolution. So in reality, very small, very weak magnetic field quickly amplified and then saturate within the very short time scale, say 1 millisecond or something like that. Then the magnetic turbulent state is realized. So after the merger, the Kelvin-Helmholtz instability are dissipated by the colliding motion of the two neutron stars. The shock wave dissipate the Kelvin-Helmholtz instability vortices. So we need another mechanism to sustain the magnetic hydrodynamic turbulence, and the possible or promising the mechanism to sustain the magnetic hydrodynamic turbulence is MRI. So this is a very schematic picture, but I don't explain in detail because this is a very textbook, easy. I think everybody knows it. But the point is, the condition for MRI is very simple. You need a negative gradient of the angular velocities. Then after the merger, the remnant is formed. So inside the remnant, the MRI sustains the magnetic turbulence state. So what we have to do is first read the so-called alpha viscosity parameter from the MHD simulation data, which is defined by the stress term divided by pressure. We can read it directly from MHD simulation. The caveat is the resolution study is essential because the numerical diffusion easily kills the turbulence. That means that you underestimate the viscosity parameter with a low or with low resolution or without the resolution study. And here is one example, my highest and longest simulation, specifically 70 meters and 200 milliseconds. For the density contour on the right hand side figure is a magnetic field strength. So this is a spiral phase, and after the merger, the magnetic field is produced by the Kelvin-Helmholtz instability. Then the hypermassive neutron star is formed. So inside the hypermassive neutron star, the MRI turns on. Then magnetic turbulent state is realized, and this system evolves very quickly, stationary up to the 200 milliseconds after the merger. This is not interesting information. Wait for it. Okay. So here's a power spectrum of the magnetic field energy density for different grid resolution, different time snapshot. In the earliest stage, 1 millisecond or something like that, the small scale magnetic field is produced by the Kelvin instability, as I mentioned, and after that, the magnet rotational instability is sustained, the magnet hydrodynamic turbulent state. However, for the low resolution case, say 100 or 70 meter case, you cannot produce a small scale magnetic field application, of course. So here is the alpha viscous parameter evolution in the core. Core is defined by the fluid element whose rest mass density is greater than 10 to 13 gram per cubic centimeter. And the different color means a different grid resolution. And unfortunately, you cannot get the convergent result, which means that the alpha parameter could be greater than 4 times 10 to the minus 3, because the highest resolution case suggests the most reliable case. But you can see that the turbulent dies away with say 70 or the 100 meter. So order 100 millisecond simulation with low resolution is unreliable. This is alpha parameter in envelope. Envelope is less mass smaller than 10 to 13 gram per cubic centimeter. In this case, the second highest and second highest resolution, I believe, is very low, which means you get not perfectly convergent, but convergent result. So, which means that the alpha parameter in this region is 10 to the minus 2. 10 to the minus 2. The caveat is we cannot judge the reliability of the simulation with one grid resolution simulation, in particular for MHD turbulent stuff. This is my message. So, because MHD simulation is super expensive, so it's not feasible to do a simulation in angular momentum transport time scale. So we switch to the viscous hydrodynamic simulation, in which you assume the viscous parameter, which is described by the alpha parameter and sound speed and angular velocity. But we know that the MHD simulation suggests that alpha is likely to be order of 10 to the minus 2. We put this value here. Then we perform the 3D GR viscous hydrodynamic simulation to find the star particles. And here is the result of our simulation. The less mass density of the remnant for the implicit case, for implicit case. Let me explain. Let me show again. So implicit case, the very asymmetric, non-asymmetric structure of the remnant neutron star survives long enough after the emergence. On the other hand, for the right-hand side figure, viscous case, the structure of the remnant quickly approaches a quasi-asymmetric structure because of the efficient angular momentum transfer. Okay. Here is the evolution for the angular velocity on the orbital plane for implicit case, for the viscous case, and different color means a different time snapshot. In viscous case, you can see that the inner part quickly approaches to the uniform rotation because of the angular momentum transport. Then the system relaxes quasi-asymmetric structures. So, what the impact of the turbulent viscosity on the post-merger gravitational wave physics waveforms? The left-hand side figure is the waveforms for the red is for the implicit case, and green and blue is for the viscous case. And you can see that it is well known that the implicit case, the quasi-periodic gravitational waves is produced from the remnant hypermassive neutron star. However, in the viscous case, the amplitude quickly approaches to zero because of the angular momentum transport. The system becomes quasi-asymmetric. Then the emissivity of the gravitational waves is suppressed very rapidly. The right-hand side figure is a spectrum, and this peak corresponds to the F2 peak, as I mentioned before. And here is an implicit no viscosity case. However, for viscous case, the amplitude, peak amplitude becomes low because the emissivity of the gravitational waves is less. So actually, the GWT17, the post-merger signal was not detected so far. So the message of this figure is a non-detection of post-merger signal can't say anything. And we need a 3G detector for detection of the post-merger gravitational signals. Okay, this is almost last slide. So how does the turbulence change the story? The open question is if peak lambda relation, the peak frequency at the merger, could be modified due to the Kelvin-Helmholtz induced magnetic field. Because the magnetic field is almost equipartition level, say 10 to 16 or 10 to 70 Gauss. So such a strong magnetic field could modify the FP. The F2 lambda relation could be modified as well due to the MHD instability during turbulence. But the question is, it only affects amplitude, as we demonstrated here, or it affects the frequency as well. So this is our question. The last one is how large is this component, wind component, because the angular momentum transport process in hypermassive neutron star determine this, determine the amount of this. To answer this question, I personally believe the 3D general relativistic neutrino radiation magnetohydrodynamic simulation is necessary, in particular with spatial, high spatial resolution and long term. And here is a recent, very preliminary recent result for the GRRMHD simulation for 1 second in 3D for binary neutron star mergers. And this is a density contour on meridian plane, X and Z plane, and this is because this is 1,000 kilometer scale. I mean, Lebanon Pacific neutron star is very small, but we can do. It is feasible to do a 1 second simulation in this GRRMHD simulation. So because this animation is long, so I will stop.
Let's thank the speaker. It was also good. Now we have time for questions.
I have one question. I do not understand why there should be any correlation between the maximum puff mass and lambda, at least with the GV 170817. The tidal deformability is mainly sensitive to neutron stars around 1.4 polar masses. So this, of course, depends a little bit on the mass ratio, but this is the region and the maximum puff mass. So you have some central density for these stars, and you could imagine having the same tidal deformability for two different equational states, and one has a high densities, some onset of other particles. Then you would have a very different puff mass, but the same tidal deformability.
Yeah, that is why they only apply relativistic mean field theory.
Yeah, but even in relativistic mean field, you have onset of say hyperons, and then you have a much lower puff mass.
But
than without hadrons, and we don't know if you have the same tidal deformability.
But the tight, we checked the data. It has a not strong, but weakly tight correlation between the maximum mass and the neutron star.
But for me, there should be no correlation at all.
Yeah, sure.
Yeah.
That is our message.
I can give you some examples. You have same tidal deformability and the tough maximum mass for one case is 2.4 and for other it's only 2.
Yes.
So there should be no correlation.
So I should say not only the relativity. They only applied a 4 kind of the equation of state. So the class of the equation of state is very limited. That is why.
What I'm telling you is without doing any simulation.
How is that?
Yeah. This cannot be.
Yeah. So for example, for APR4 equation of state case, the radius of the neutron star is small, but maximum mass is high, right?
Yeah.
But in this case, the large maximum mass means large neutron star. That is what I want to say.
We have
So you were saying that there are arguments to say that the black hole is formed in seven, just energetic arguments, but apart from these arguments, which I personally don't feel are extremely solid, but apart from these arguments, are there arguments from the simulations indicating that really a black hole was formed in the sevens?
No. So it's quite hard, the time scale to, of course it depends on the equation of state or model, but according to our experiment for the DD2 equation of state, the remnant doesn't collapse to say 10 seconds. It's a very, very long time simulation. For the SFH equation of state, it collapses to say less than 100 seconds. But 200 second simulation is not feasible. So it's super hard to answer this question from the simulation. Only the energy side.
With that, let's thank the speaker for an excellent talk. So now it's time for coffee break, which is just outside here.
No.
So, it's better to talk over here so we can put it
Yeah.
in the microphone.
Yeah. And you have a change.
Yes, we do.
Yes.
Okay. Czy już ta sesja?
prepare yourself? You want to be the chairman for all the talks?
No, we will already.
Because if that will just
Sorry.
because you teach lectures to
Someone will already. I'm here.
okay, then I'll go on.
Already not in.
Just to try everything.
So yes, it seems to be. Laser
Yes, those two. So it's, yeah. Well, it's not a problem. I'm used to it.
So I think the best location is right here.
Yeah.
So you're close to the microphone, and
Okay.
they can pick up your voice. You can pick up your voice as well.
Yeah.
Yes, and you can look, and everybody can see. And if
Yeah.
they don't see you, they can just move the whole surfaces. So I think this is ideal place.
Okay.
Yeah, we have 5 minutes. So.
Yeah.
A little bit one. Okay. Oh, yes. 5 minutes. Okay. So we have 5 minutes for It's days. I think we will still have to come. I already told to invite the friends. Yeah. Well, actually, we had decided based on people who expressed interest. I was
Yes.
in Sweden. We
Okay.
planned the budget for 30 people.
Okay.
На паузе. Я сейчас стоит на паузе. А, все, это просто надо нажать, да? Вот это? Звук отключен. Okay, awesome.
It was a very early.
Anissa was also interested. Yes, it was very early.
Это просто запись. А по ней трансляция идет.
А, все. Трансляция, оказывается, не остановилась.
Не, она идет, да.
Все. Да, все хорошо, когда начинаем. Okay, so our next speaker is Michaela Ortel. She will talk about neutrino-nucleon interactions in a hot dense matter.
Okay, so yeah. Thank you. So I will talk about neutrino-nucleon interactions in dense and hot matter. This is a topic which is discussed for already a very long time in the CoCoNuT connection and context, and also I think it's very important for the binary neutron star mergers. But from the strong interaction point of view, this is far from being easy, and I will have a relatively long introduction. So if you already know everything I will show in my introduction, and please interrupt, I will go ahead. And the idea is that you have, because neutrinos, they are not in equilibrium with matter. You have some neutrino transport, and you have some, in the source terms of your transport, you have some interaction rates of the neutrino with matter, and they are far from being well known. And so I will have my introduction. Then here, for the present time, I will concentrate on charged current neutrino-nucleon interactions, and then I will show some preliminary results and numbers. So why are we interested in these neutrino interactions? So I think you know all for this core collapse supernova that we have since 25 years this scenario of a neutrino-driven explosion mechanism, and at least for some of the models which are at the border of exploding, with small changes in this interaction rates can decide whether we have an explosion or not. And then the neutrino-driven wind is very important for the nucleosynthesis, and also the essential cooling mechanism of the protoneutron star, contracting and becoming a neutron star, is by neutrino emission. And if we look at binary neutron star mergers, because again we have a very neutron-rich and hot environment, so we have an intense neutrino emission, and the neutrino reactions determine also the neutron to proton ratio, so the electron fractions. And so electron fraction in the ejector, you just heard in the previous talk that this electron fraction is a key ingredient also to decide about what happens in the ejector for the heavy element nucleosynthesis, for the R process. And again, here you have a cooling effect, so you release energy via neutrinos, and also you have some effect of energy and momentum exchange with matter. Fourth point is, if you look at older neutron stars, still neutron star cooling is dominated by neutrino emission for a very, very long time. In principle, you have energy loss by neutrino and photon emission, but the neutrino emission is the dominant source of energy loss for a very long time, about, say, millions of years. And so this is the reason why we are interested in neutrino interactions with dense, well, here it's cold matter, but for the two other scenarios, also hot matter. And this is not really very easy to describe in a precise way. There are different types of neutrino interactions with matter. Matter is composed of nucleons. Well, you can have other particles such as hyperons, but here the formalism is the same if you have other baryons, but I will concentrate here on nucleons. Then you can have on nuclei and of course on charged electrons. and photons, you have the different types. You have the scattering, which is via the neutral current. Then you have absorption creation processes. This is via the charged current. And you have pair creation process via the neutral current. And here I've listed some typical reactions. So the first two, these are the electron capture process. And the second one, well, it's more or less neutron decay. Then you can have the same type of reactions on nucleus, I show here. So A is the mass number, Z is the proton number of the nucleus, and it corresponds to the same type of reaction as this one, except that the protons and neutrons are bound in the nucleus. Then you can have these type of these scattering reactions, and also this type of reaction. So here, what I will concentrate on is the charged current reactions on nucleons. So the two first reactions. So what are the thermodynamic conditions we have to consider? Because I say hot and dense matter, but how dense and which temperature I should consider for calculating my neutrino matter interactions. So if you look at quark collapse and binary neutron star mergers, so if the emission is mainly from the dense and hot central parts, so I should look at the neutrino opacities close to the neutrino sphere, because these are those which determine mostly the proton to neutron ratio of the ejector, and also the efficiency of the neutrino heating mechanism. And the conditions are relatively similar for both, except for the binary neutron star matter. You have more neutron-rich matter, and typical neutrino energies are of the order of tens of MeV. And of course, for neutron star coolings, conditions are different because you have much colder matter, and here you can say the neutrino emission is typically is from the core, but for cold matter, and the typical neutrino energies of the order of the temperature. So here's in this table I have a summary of the different conditions of the barrier number, densities, which you have for typical temperatures, and electron fractions I should consider for where I calculate the neutrino opacities. Then how to calculate these neutrino nucleon reactions? So the basis is just the charged current weak interaction. So I've written it. So this is written in the Fermi form. So already, because in principle from the standard model of weak interaction, you should consider propagation of W boson. But here we are at energies much below the mass of the W, so we can write it in the form which in 1934 proposed for the beta decay. But here the important point is, so the basic interaction is on the quark level, but we need the interaction with the nucleons. So this type of interaction term governs all these type of reactions, where of course you have the reaction itself, so electron capture, and you have the inverse, and you have also the electron and positron capture reactions, and neutron and proton decay, and they are all governed by the same type of interaction. Of course, all these reactions, they are not equally important under the different thermodynamic conditions, but if you calculate the reaction rates, you can do all of them in the same manner. And the main problem is, as I said, you have the interaction with the quark level, and you need the interaction at the end with on nucleons, and not only just on the free nucleon, but on nucleon which is in dense and hot matter. So the main difficulty is here that you have to calculate the matrix element where you have this charged current on the quark level, and at the end you have a nucleon state and a nucleon state in a dense, strongly interacting matter. So schematically, you can write that this is the general form. Here, written the so F nu. It's the so it's here it's for this electron capture process, but it's very similar for the others. So here you have the change in time of the neutrino distribution function. It's proportional. So here the time of the neutrino distribution function. Then you have the electron density, because if you want to capture an electron, because you need the electron density, then you have a tensor which describes the lepton part, dynamics of the lepton part, and then the most difficult part here is which contains all the nuclear part. This one here contains so a nuclear matrix element and a phase space. So during the last several tens of years, different approximations have been proposed and are used also in the simulations to calculate so this nuclear part composed of the matrix element and the phase space. The most basic approximation, I would say, is called this elastic approximation. You find it, for example, in Brünn 1985 paper. So where you approximate the nuclear matrix element just by the expression for nucleons in vacuum. So you have two channels. You have the vector and the axial channels, where you take just two constants, GV, which is just 1, and GA, which is the axial coupling, which from free neutron decay has been determined experimentally. And as you take the nuclear matrix element, just the vacuum, well, you should just take the value which has been determined from free neutron decay. And you neglect momentum transfer to the nucleons. For the phase space, you have non-relativistic kinematics, and you do not consider any nuclear interaction. This means that for the phase space, you take the free nucleon masses and also the energies. And so if you look at the energy which is transferred to the nuclear medium, if you have one reaction, it's just so you take the difference in electron energy, neutrino energy, just the difference of the free neutron and proton masses. And if you do this approximation, then you can calculate to get simple analytic expressions for your neutrino-nucleon interactions, which you can easily use in any simulation. So then, during the years, different improvements of these basic approximations have been proposed. So the first one, if you consider corrections to the matrix element, so you do not consider the matrix element in vacuum, but the most, it's not only that it's in vacuum, but you just take the most simple expression. But because if you look at the Lorentz structure of this matrix element, you can have different terms. And one of them is, for example, this big magnetism correction, which is also present in the vacuum matrix element, and which is proportional to the difference of neutron and proton anomalous magnetic moment. So this is principle relevant at any density, can be included into the expressions. Then another correction you could consider is that you take into account this the nucleon internal structure corrections via momentum dependence of this form factor. They are called form factors, this GV and GA. But if you say that if you know that this nucleon internal structure should be important at an energy of the order of 1 GeV, this corresponds to the nuclear mass, so typical energy scale is 1 GeV. So for the relevant energies we are concerned with, this is a very small correction. So if you include this, then you get still simple analytic expressions, which you can put into the simulation. Then you can consider a more sophisticated treatment of phase space. So take the momentum transfer to the nucleon account, and also use the full momentum dependence of the phase space. If you do it, say you can develop it in the neutrino energy compared to the nucleon mass, then you still can develop analytic expressions. But if you want to do the full treatment of the phase space, then you end up with numerical expressions. But this is rather straightforward and can be done too. But this is still not the end of the story, because here we are concerned with a hot and dense asymmetric. So asymmetric means you don't have the same number of protons and neutrons matter. So we need to consider also nucleonic correlations. If we taking the matrix element just in vacuum is not sufficient. So the most simple type of correction in this sense is that you consider mean field corrections, meaning that you say, yeah, each nucleon is moving in a mean field of all the other surrounding particles. So this is known from atomic physics. So you take this into account, and this technically you get some interaction potentials. So the nucleon, the energy of one nucleon in the medium is not just p squared over 2m, but you have an interaction potential in addition. So this is written here, so for neutron and proton. So this is the simple non-interacting kinetic part, and then you get a potential. And here also you have some effective mass for the nucleon in the medium. And the effect of this correction is that here for the transferred energy to the medium, it's shifted for these charged current reactions. So here you have no longer the masses from vacuum, and in addition you have the shift from these interaction potentials, which in dense asymmetric matter can be relatively important. And so this induces, because this difference has of course an opposite sign if you look at neutrino or antineutrino reactions. So this increases the difference between neutrino and antineutrino reactions. And from these two papers, say the main conclusion is if you include these mean field corrections, then you can get a neutron-rich ejecta possible in neutrino-driven winds of Koch collapse, and this, of course, has consequences for the nucleosynthesis. And as an example, this is from this paper here. What is shown here is a comparison of including or not these mean field corrections into the neutrino interactions. So the red lines correspond to the results without the mean field corrections, and the blue lines with the mean field corrections. So here you have the neutrino luminosity and the mean energy as a function of time after bounce. And here you have the electron fraction at the end, 2p per baryon. See that, well, these corrections, they can have important consequences. And then again, this is not the most, say, realistic way of treating the nucleon correlations in matter, so the nucleonic interaction in dense matter. But you can go beyond this mean field approximation. And the first papers which have shown that what is called the so-called random phase approximation can have a very important effect on neutrino interactions in dense matter are already 20 years ago. People show that the difference in the reaction rate can be 1 order of magnitude for the relevant conditions. So what is the idea of this random phase approximation is just that you not only take your mean field, but you sum up some, I call it particle hole excitations. This means you have the Fermi sea of your nuclear matter, and the hole is, you mean to put a particle above the Fermi sea, and the particle is that you just have an excitation of a particle in medium. So again, you have the vector and the axial channel, and this type of approximation is widely used in nuclear physics to describe resonances of nuclei. For example, this, what I show here on the right hand side, this is for the giant dipole resonance. So meaning if you take a nucleus and then you imagine oscillating neutrons and protons against one against each other, and you will see a comparison of a calculation using this random phase approximation and the experimental data, and you see that this approximation in many cases well describes the experimental data for in nuclear physics. And if you go to low densities, then it reduces just to infinite. So it's really an approximation which takes into account correlations at high density. And what has been shown already 20 years ago is that you get really a strong suppression of neutrino opacities and energy-dependent enhancement suppressions for antineutrinos, which we'll show later in the results. And what people did then is that they defined some global enhancement or suppression factors which have been included in some of the simulations for the neutrino reactions. But I will show, if you really want to include this effect, then you should include the energy dependence of these reaction rates. And now I will show some of the results using the different levels of approximations I just explained for different conditions. So here what I use, well, one particular equation of state, and this is shown for some typical conditions. So here it's more neutron-rich matter, so it would be, say, more for the binary merger case. And what is shown here, so you have the opacities, so say the inverse in-free path for neutrinos on the left, antineutrinos on the right, as a function of the neutrino antineutrino energy, and the different curves correspond to. So this dotted line is the basic elastic approximation with free nucleon masses and no interaction potential. This line, this dashed line here, corresponds to the approximation where you take the same elastic approximation, but you replace the free masses with the in-medium effective masses, and you take the interaction potentials into account. And this line here, so the solid line here, is if you take into account also the full phase space. And in this non-relativistic full phase space, the red line is if you have a relativistic phase space. I will say a word about this later on. And this black solid line with the dots on it corresponds to the random phase approximation. And so what you can see here, so indeed the random, so first point is including the full phase space. If you have the mean field corrections, then including the full phase space, it's only a small difference with respect to the analytic elastic approximation where you just enter your potentials and effective masses for most cases. So again, for both neutrinos and antineutrinos. Then here you can see what I said before, you have the RPA correlations have a large suppression. It's 1 order of magnitude for these conditions for the neutrino opacities, and at very high energies they approach one each other, but for the relevant energies which are in this region, it's 1 order of magnitude suppression. And for the antineutrinos, what you can see here, well, you have this pronounced minimum in all the curves, which correspond to reaction threshold. And what you can see here, so this minimum, this reaction threshold from the vacuum without any nuclear interaction, and the mean field correction will have a shift to much higher energies. And this shift you can understand, it's just the difference between the neutron and proton potentials. So here you can say you have the minimum here and And the same is confirmed, yeah, if you have the phase space, of course you have no shift in this energy of this threshold. But if you include the RPA correlations, then you have a slight reduction of this shift of the reaction threshold. And what you can see for the antineutrinos, you cannot define any global factor between the RPA results and the mean field results, because it's very much dependent on energy, and in particular you have this shift in the energy of the reaction threshold. So here, what I said before is confirmed. Here is just shown for some less neutron-rich conditions. So yeah, of course, if you have some less neutron-rich conditions, then the shift in the reaction threshold is less pronounced, because the difference between the neutron and proton potential is less strong. So you can see here the shift is smaller, but again the same conclusion is true. And well, the results I show here, they are in agreement with other results doing the same type of approximation. And what here I said before, I will say a word about this relativistic. So here you see very strong special relativistic effects on the phase space. I should check, because for me this is too big an effect just from special relativistic treatment. They are in agreement with this paper, but in this paper they said it's because in the uses a relativistic mean field equation of state and gets very low effective masses. So they are of the order of just 50-100 MeV. So it says, well, the special relativistic effects, they are so important because you have so low nuclear effective masses. But here I have another equation of state, where the effective masses are still 700 MeV. So this cannot be the same effect. So I don't really believe for the moment that this special relativistic effect is so strong. So this has to be checked. But for the others, it's in very nice agreement with what we expect from the physics behind. And you can see also that if you go to low densities, where you would expect all these effects of the nucleonic correlations to disappear, because you get to more dilute matter, then all the different approximations, except for very low neutrino energies, they come very close one to the other, with confirmation that this is very consistent with what we would expect. Now, I said the idea is that you have this very strong effect from the RPA correlation of one order of magnitude, and this is known since 20 years. And then what people did is, because it's in the simulations, if you do, say, depends a lot on the thermodynamic conditions, but doing such a curve for different neutrino energies already takes a lot of time to do the calculation of the reaction rate. So you cannot do on the run the numerical integration of matrix element and phase space to have the reaction rate. So what people did is they took these analytic approximations and put some correction factors. But as this is not very, let's say in particular for the antineutrinos where you have the shift, and also you have, if you take the analytic approximation, here really it goes to zero, the opacity. Whereas here you can see the minimum is much less pronounced. So you really need some correction depending on the energy. So the idea here is that you do an interpolation of a fit, polynomial fit to the results for the reaction rates, and provide so then just the coefficients of the fit such that you can use them in simulations. And so here I show one example of how this polynomial fit is done. So the dot corresponds to the points where the rate has been calculated, and the line corresponds to the fit. Of course, there should be some ideal thing not to store too many coefficients, because you have all the different temperatures, densities, and electron fractions where you should store your coefficients, and then in addition you have this dependence on the neutrino energy. So you should find a compromise between the number of points you take for your polynomial and the precision which you get for your fit. So, and here you can see a case where it's the polynomial fit is not really obvious, because you have on a very small interval you have a strong change. So here it's a logarithmic scale, a strong change in the intergrid, because due to this reaction threshold effect. So here, as you can see, you need a lot of points to really interfit correctly the reaction rates without having any Gibbs phenomenon. But I would be happy to discuss with people who really do the simulation, if you have better ideas of how to provide the results and what would be the best thing, how to make it useful for the simulations. Yeah, so the idea is not to end with just these charge current reactions, but at the end to do this for consistent with the underlying equation of state model, not taking just one reaction rate taken from one equation of state, but provide these coefficients for the different equations of state, which could be used together with the equation of state tables. And what is done here, so well, this is perhaps not so important for you, but also what I calculated with the full isospin breaking corrections, meaning that in the expressions they used 20 years ago, they did not include all the corrections which depend on the mass difference between neutron and proton. But in asymmetric matter, this can be important because it's mass difference is large. Then can choose between different levels of approximation, just phase space, or including also RPA correlations. And so before corrections are energy dependent. And here these are just some first results where show that the scheme in principle is working. And here it's one calculation of the infall phase. It's with the CoCoNuT code where you compare the elastic approximation, so analytic, with mean field corrections and with full phase space. Of course, it's just showing that the simulation with the scheme is working. You do not, during infall, the electron fraction nuclei is much more important than the nucleons, so that both of them give more or less the same result. So it's the electron fraction as function of the baryon number density, and so that it's more or less the same means that the scheme is consistent and is nicely working. Of course, we expect in the after bounds, we expect much more difference from these reactions on nucleons. So here, I just leave you with a summary and the outlook.
Questions?
So I have a question in last figure.
Yes?
So this is a snapshot, right?
Yes.
What?
No, it's not a snapshot. It's
Evolution?
for the evolution during infall. So it's parameterized with the baryon number density of the electron fraction.
You can see that,
Well, sorry, I didn't explain. So here you have electron fraction, here it's 0.44, here it's something like 0.3. And here you have baryon number density from, maybe it's 10 to minus 4, 10 to minus 1.
Okay.
So it's parameterized. The evolution, thermal evolution is.
This includes the
Ten-
after the bounce.
No, this is just during the infall
Infall.
epoch. Yeah. And I said that you have only a small difference is because what is important here is on nuclei and not on nucleons.
Yeah, I'm interested in how large the impact of the RPM approximation.
Yes,
Yeah,
this
neutron,
we
neutron velocity.
we don't have yet because well I would like to have it, but for the moment because it takes also a lot of time to calculate all these interaction rates for the full range of temperatures, and so I'm still calculating.
Yeah, I have one question. So, what is the range of the table from density in terms of density?
It's the range of the equational state table.
Because sometimes you need a very low density region for
Yes.
follow the ejector in binary case.
Yes, but well, in the very low density region, all these corrections would be very small.
Yeah, small.
So one possible thing would be that you have these neutrino reaction tables only at high densities, and at low densities you use some analytic approximation because, as I showed here, you see it doesn't change a lot, and this is not even the lowest density you could have in. Yeah. But for the moment, what I do is I calculate the table for the same range as the equation.
Do you have other questions?
So you were asking about how to provide these things.
Yes.
I think the best thing is tables rather than
Yes.
polynomials.
So as tables,
I think
but the tables would be four-dimensional because you need the neutrino energy.
yes, but I mean we have to check the size of the tables, but maybe it's not that bad. I mean, the thing is that tables is the fastest to evaluate.
Yeah,
Because
but
if it
how,
is-
for
if it
example,
is-
in this case, how would you, which energy would you choose? And you could not even choose for each temperature, density, and electron fraction. You could not choose the same grid in neutrino energy because you see this this threshold would move. And if you want to have some good description of this threshold, then you say at this condition you put a point here, and if you have here another condition, you should meet it here. Yeah. So I don't think that tables well, we can discuss, but for the moment I think it's not.
So I wanted to ask about this. How high in order are these polynomials, and how large are typically these polynomial coefficient tables?
So what I have shown here is a ninth order polynomial. Yeah, and it's a compromise you have to find between the precision of your fit, and so and then it's a ninth order polynomial, but you choose some energy domains, so it can be that for some temperature and so some particular condition, you have, as a function of neutrino energy, you have more than one domain. So if it's just a function like this, then one domain would be sufficient, so you have 9 coefficients. But if you have a thing like that, where you have, here you even have 2 threshold behaviors. One here, this is because the RPA collective excitations enter this, the kinematic region of your phase space integration, and here it does not enter anymore. So here you have one threshold, and here you have the physical, the reaction threshold, and then you have here which resembles a little bit like that. So then you need more than one domain. So it depends really on the thermodynamic conditions. So the typical size, I don't remember for the.
But in typical, you don't have that, 100-degree polynomial with 200.
No.
Okay, just
Last question.
answer to Pablo's. From this polynomial, you can generate tables in a very reasonable time.
Of course.
If you want
Yeah,
a table,
yeah.
then you can generate it.
Yes, I know.
Yeah.
But
This is
so
why
if-
I said I'm open to discussion. Now I have the data, I have the polynomial, and so it's easy to transform to other forms of
Can you go to the next slide so I can write down the addresses?
You can.
this one.
No, the last December slide, I just write down names.
Well, we'll send the slides.
Okay.
We have to.
Yeah.
So if you have thresholds, you can do tables anyway. Because if you know the thresholds, you know that between the thresholds it should be smooth and you can.
No, the point, well, now I know the threshold because after having done the calculation, I know the threshold. But the difficulty is in advance, I do not know exactly where the threshold is. I show here. Here, I know exactly where the threshold is for the unlimited expression. Here, I know too, because it just shifted by the potential. But for this calculation, it's shifted a little bit below, but I don't know of how much.
So you have to do this one
Once,
by one. I mean,
yeah.
one by point.
One by one, I have to look where is exactly the threshold.
So this is a lot of work.
Yes. This is why I have not yet finished.
Okay, let's have the speaker again. So, next talk is by Aurelian. He'll talk about constraining equations of state of neutron stars using method of probability and constellations.
So we'll have to open this one. Let's go. This one. Let's do it. Okay, wait. Let's open from here. Go down. This one. This. Yes, you know. Let's wait. Let's wait. Let's go after this.
Good morning, everyone. Thanks for the introduction. In this talk, I will present two recent projects which aim at constraining the equation of states of neutron stars from their gravitational wave emission. First, I will talk about tidal effects in binary systems. In particular, I will show how the tidal deformabilities, which has been inferred from the GW17 0817 event, can be used to get some valuable information on the equation of state. So this is a work which has been done in collaboration with people from Brussels, so Nicolas Chamel and Loïc Perrault, a master student. And then I will present another project which we have recently started at the Paris Observatory with Jérôme, Michaela, and master student about the numerical modeling of neutron star oscillation with spectral methods. Let me first recall some very basic feature of neutron stars. So, as you know, neutron stars are very interesting objects because of their very peculiar properties. So indeed, these stars are very dense with average density much higher than those found in nuclei in laboratory. They are also cold, at least for old enough neutron stars, and mostly made of neutrons. And actually, these physical conditions are very different from what we know from on Earth, and they are so extreme that they cannot be reproduced in the laboratory. So for these reasons, the exact composition of a neutron star remains poorly known, especially for its inner core. So one of the main ingredients we need to model this star is the equation of state, which relates pressure to the density, and which depends on the composition of the star and of the interaction between its constituents. So since these two aspects are poorly known, several equations of states have been suggested, and each of them can be characterized by its corresponding mass-radius relation. So indeed, one can use electromagnetic observation to get some constraint on this plot. So far the best constraint we have come from pulsar timing observation, which have shown the existence of very massive neutron stars. So any equation of state which fails to reproduce such massive star can then be ruled out. We also have some observation about constraint about the radius of a neutron star from their thermal emission or X-ray burst in low mass X-ray binaries, but these constraints remain quite uncertain. So until 2017, the only constraint we had on this mass radius relation came from electromagnetic observations. And with the recent opening of the gravitational windows, indeed, the constraint we will have on this relation will become rapidly more and more stringent. So since these neutron stars are very compact, they are excellent emitters of gravitational waves, and this is something very good because since these electromagnetic and gravitational waves have different properties, they will carry complementary information on their sources. So different events can lead neutron stars to emit a large amount of gravitational waves. So the best one, the most famous one, is the neutron star merger, as was first detected by Advanced LIGO and LIGO. We could also mention collapse supernovae, pulsar glitches, or the possible presence of some permanent symmetries, which are sometimes called mountains. And in the following, I will first focus on tidal effects in this system, and then I will talk about neutron star oscillation that could be exciting during these different events. So as you all know, and was nicely summarized this morning by Linda, first direct detection of gravitational waves associated with a binary neutron star merger was done on August 17th of August 2007 by LIGO and LIGO. And the first signal that was received on Earth was the gravitational wave signal, which is plotted here. So this is the frequency as a function gravitational waves were actually detected in association with post-merger orbits. So two seconds later, short gamma reverse was also detected by integral and Fermi in association with this event, and later, a few hours and days later, another electromagnetic counterpart, so-called kilonova, was detected and followed by several different instruments. So the joint analysis of these different observations has brought valuable information on the formation of heavy elements through their process, also on the fundamental physics concerning, for instance, the speed of gravity or the Bell's constant. And it also gave us some interesting information on the stellar structure of the neutron star that I will now discuss. Okay, so the idea, as you know, is that during the last orbits preceding the merger, the neutron star gets closer and closer, and they become increasingly deformed by the combined action of their own gravitational field and the gravitational field of the companion. So these tidal effects are accompanied by an average coefficient, lambda or lambda tilde, that has been measured by the LIGO-Virgo collaboration. So this coefficient depends on the two neutron star masses and the two individual deformability coefficients, which depends on the stellar structure and thus on the equation of states. So by having some constraint on this individual tidal deformability, we could expect to get some constraint information on the equation of states. So by comparing the gravitational wave signal with various templates, the LIGO-Virgo collaboration was able to get some constraint on this individual tidal deformability that are plotted. So actually, three different methods were used. So to compute this theoretical waveform, so first one in which the masses and the individual tidal deformabilities are treated separately. Second one in which these quantities are related by some universal relation, and a large third one in which a large set of parameters in the equation of state were used. And as you can see here, so the three methods essentially give similar results. So the 50% most credible values are here, delimited by this H line, and the 90% levels are plotted here with boundary with plain lines. So indeed, it's now very tempting to compare this data with preferred equation of state. So as what we did is to focus on the PSK equation of state, which are developed in Brussels and Montreal, and which are interesting because they are provide a thermodynamically consistent treatment of all the regions of the star within the same model. So from the stellar surface to the inner core. So these equations of state are based on functional that were precision fitted to essentially all experimental atomic data and were simultaneously adjusted to also some theoretical data. So in this work, we focused on mainly four BSK equations of state, so 22, 24, and 25, which mainly differ in their prediction for the symmetry energy coefficients at saturation, which are fitted to the same neutron matter equation of state. So these three equations of state can be used to study the impact of the symmetry energy on the tidal deformabilities. And we also focused on BSK 26, which is fitted to the same symmetry energy coefficient as BSK 24, but to a softer neutron matter equation of state. So we could study the impact of stiffness of neutron matter equation of state by comparing these two equations of state. So here are the corresponding mass radius relations, and as you can see, all these equations of state are consistent with the two solar mass measurement of neutron stars. So here are in black, the line in black corresponds to individual tidal deformabilities for this particular equation of state and for chirp mass corresponding to those inferred from GW 17 or 18. So by comparing this equation of state, one can compare the influence of the impact of the symmetry energy on the tidal deformability. So as you can see here, this B scale 22 with the highest symmetry energy coefficient seems to be marginally consistent with this method and rolled out by the other one. So should it mean that this equation of state with such a high symmetry energy coefficient should be appears to be disfavored.
This is 90% control.
This is a 90. This one.
I don't know, your equation is your ESA, or you just calculate the tidal deformability.
Sorry.
You just calculate the tidal deformability.
Yes.
Ah, okay. You didn't do the Bayesian analysis.
No, no, no.
Okay.
We also, so one can also study the impact of the neutron matter stiffness by comparing so this equation of state, 24, 26, and we also actually used an older BSK equation of state. So this other equation of state was actually discarded because it cannot support two solar mass neutron star, and it was fitted to a very soft neutron matter equation of state. So actually these three equation of state are so fitted to different neutron matter equation of state with different stiffness. So the softest one is there and the stiffest one is there. And as you can see, among all the equation of state we consider, the only one we actually lie within this 50% credible level is the softest one, so which also support, as was already mentioned by Kenta, that the gravitational wave data alone tend to favor the razor soft equation of state and density relevant for this neutron star which we are detecting during this measure. So besides these constraints on the tidal deformability, some other constraints could have been obtained on the mass radius relation. So first, the analysis of the electromagnetic observations suggest that the remnant of the merger did not collapse directly into a black hole, but only after a given while. So this means that the total mass of the binary should be lower than some threshold mass constraint, which can be rewritten as a lower limit on the radius, which are put in here. So this is the work done by Bauswein and Kokel. By using further assumption of the life timescale on which the remnant collapsed into black hole, different constraints have been reached on the maximal mass of a non-rotating neutron star. So here I only plotted a kind of conservative limits given by these different studies. So far, these constraints are not so stringent, because it means that the maximal mass should be probably between 2 and 2.5 solar mass, but we could expect that this limit should improve with further detection. We also note here that there is a kind of lack of consensus about the lifetime during which this neutron remnant survive after the merger. And then the constraint on the tidal deformability, so coming only from the gravitational wave signal, was also reinterpreted as constraint on the radius by the LIGO-Virgo collaboration using two of their method I previously mentioned. Okay, so as you can see, especially for this constraint on the radius, these different constraints tend to be more stringent than those that we previously had from only electromagnetic observation. So among these different equations of states, all happens to be consistent with the constraints except BSK 19, which actually predicts too small radius and masses. Okay, so let's now move to neutron star oscillation. So, as I said earlier, so different events are likely to excite oscillation modes, which can in turn emit some gravitational waves. So since this oscillation mode and the corresponding gravitational wave emission will depend on the structure of the star, we could expect, by future observation of these gravitational waves, to get some constraint also on this equation of state and to probe the interior of neutron star, as we actually do for the Sun from indeed electromagnetic observation. So our aim is to compute gravitational wave spectra associated with this pulsation, so for isolated neutron star, for a whole set of unified equation of state as BSK1 ones that I mentioned earlier. So we just skip this one. So contrary to what is traditionally done, we do not compute this oscillation mode by using some perturbation theory, but we rather solve the time evolution of the nonlinear equation governing the dynamics of the matter of the space-time. So this is quite similar to what was done in 2006 by Dimmelmeier et al. Okay. So in this seminal work, they study some nonlinear axisymmetric pulsation of rotating relativistic star, so with the CoCoNuT curve, for a few polytropic equation of state. So as I said, so this is a very recent project, so we have started not a long time ago. So so far the code is only based on Newtonian gravity in spherical symmetry and makes use of polytropic equation of state with an adiabatic index of equals to 2, for which an analytic equilibrium configuration can be found. Okay, so indeed these assumptions are very, very far from reality, but this simple case can be used to check the accuracy of the code and to implement various techniques that could be useful for the following. So the equations that are solved are the following. So, okay, so standard equation and continuity equation, Euler equation, and Poisson equation for the gravitational field. And these equations are solved by by the polytropic equation of state. So indeed, some boundary condition that the stellar surface should be specified. So we implemented two possible choices, which are mathematically equivalent. So either to assume that the density of the surface remains constant, or either that the divergence of the velocity field remains vanishes at any time. So the idea is to use a spectral method. So to solve these different equations. So this spectral method consists in expanding the spatial part of any function in terms of Chebyshev polynomial. So indeed, all this code is implemented in the Lorraine library, so as to benefit from all the pre-existing routine. And the idea here is to use a spectral method to solve all these equations. So matter equation, integral equation, and a gravitational field. So this is quite different from what was done in Dimmelmeier et al. And what we expect by using a spectral method to solve all these equations is to reduce computing times, which would allow us to explore the impact of various equation of states on the oscillation spectrum. So we use also a moving grid adapted to the stellar surface, and the time integration is simply performed by a third-order Adam-Rochefort method. So it's explicit method, and we have to pay attention to the CFL condition. Okay, so the oscillation modes are excited as follows. So we start from an equilibrium configuration. Then we put the star slightly out of equilibrium by inducing some perturbation in one of the free variables. So for instance, by using a kind of initial perturbation in the velocity field. And then we follow the time evolution of the free variable we want. So for instance, this is an example of giving the time evolution of the central density, okay, for this particular parameter. You can also plot the radius and so on. And the accuracy of the code is measured by plotting the non-conservation of the total mass and total energy of the system, so as a function of time. And as you can see, these the accuracy remain quite good, even if the number of collocation points used here is not that big. It's only 20, 25. So then one can get the eigenmodes by using Fourier transform on the time evolution of some variables. So here I have plotted the Fourier transform corresponding to the central density, radius, integrated density, and integrated velocity for this stellar configuration and for this initial perturbation, so linear perturbation. And note that here the amplitude of the perturbation is very small. So different oscillation modes are excited, and all the different Fourier transform give the same results, which is nice, as expected. And we also check that the different eigenfrequencies that we obtain are in agreement with those from the previous work. Then it's pretty interesting to study the impact of the amplitude of the perturbation on this spectrum. So here in the Fourier transform of the central density for parameters corresponding to similar to this one, so with an initial perturbation, linear initial perturbation, with a very, very small amplitude. Okay, so in this case, only linear modes happen to be excited. So let's now increase this, the amplitude of the perturbation. Okay. So as you can see, as long as the amplitude becomes increases, the new modes appear, and the spectrum becomes richer and richer. Okay, so actually, these additional modes simply highlight the nonlinearity which are present in the nonlinearity which is present in the Euler equation, and this additional peaks simply arises from linear sums or differences from the linear mode which are indicated here in black. Okay, so indeed the non-linearity are present in this evolution. Okay, and so finally we also implemented eigenfunction recycling technique that was also proposed by Diemenmayer et al. And whose idea is to excite only one specific eigenmode we would like to study. So the idea is the following. We start by an initial perturbation which excites many different modes, and at least the eigenmodes we would like to study. So for instance, the fundamental mode here. Then from this first run, one can extract the eigenfunction. So here in blue, this is the eigenfunction with respect to the radial coordinate here. So in blue is for velocity, in orange for the density. Then one can use this eigenfunction as an initial perturbation, a new initial perturbation for the code, so to make a new run. And as you can see with this eigenfunction, one can mostly excite the fundamental mode we want to study. And if we want to get rid of this harmonics, one can simply iterate the process, and with the second one, you can see in blue that these harmonics did appear. So far, just to conclude on this part, the second part, so the results happens to be quite encouraging, but indeed this is a very, very naive case, so we plan to provide different improvements of this code. We are now currently working on using a GR equation instead of Newtonian productive. We also are working on using equilibrium configuration given by other code from URN, and also realize these simple spherical symmetry assumptions. Okay, sorry, I forgot it. So it was just an illustration of the eigenfunction recycling techniques where I took the eigenfunction in velocity for the fundamental and the 7 first harmonics and the corresponding Fourier. Okay, so just to conclude, so neutron star unique cosmic laboratories for studying matter under extreme conditions, and actually, as we have seen a few examples, studying their equation of gravitational waves emission can be shed light on their interior. So so far, we already have some interesting constraints on the equation of state from these unique events seen by the LIGO and Virgo detectors, and also from their electromagnetic counterparts. And let finally mention that since April this year, so the LIGO and Virgo are currently in their third observation run, and you can find a list of possible candidates in this website. Thank you for your attention.
Any questions?
So is it easy to extend the 3D? Because you find out, sorry, later part of the talk. So your final target is hypermachine. Not.
Yes, I mean, we indeed plan to study it in 3D, and yeah, in this case it would be a bit different because we would have to consider different numerical grids for the hydro parts and the metric parts, but it has been already done, so probably it would be not so difficult.
A question on the first part. So, one of the big advantages of the Brussels coordinate state is that they are unified in the sense for the crust and the core use the same interaction. Then you know that for the neutron star radius, this is a very you have large differences in the plane radius using a unified or a non-unified one. Have you looked on the effect on the tidal deformability using comparing unified and non-unified equations of state?
No, but what we are currently working on is to study. This is very related to your question. Is to study the impact of using one of BSK equation of state and one other in which we forget about the crust, but we simply use the same functional from the core and until only homogeneous matter from the core to the crust.
But what you could do also take your BSK for the core and then use of some standard matching procedure and
This is yeah. But the idea was to just not to use matching, but to use the same.
An idea of the quality of all the
Yeah.
results with the matching.
This is we are currently working on.
Okay, we have a question. Yeah.
The lifetime of neutron star before merger is about 1 seconds.
Sorry.
What is the lifetime of neutron stars before merger?
Before.
7 seconds.
Before
You show
merger?
that. Yeah, you show that.
When they are in spiral phase, because it can last for.
You mean before the collision, right? Before the
Before the
expire.
collision.
I mean, it's millions of years.
Yes.
You show the plot.
Yes.
1 2 seconds.
No, it's millions of years, right? It's a long. But after measure, it can be 1 2 seconds, right?
Yeah.
So before measures, they are 4, but once they measure, they are 4.
I would like to ask you, so when you show low frequency mode, which has about 5 hertz, is it correct to consider this low frequency mode
In my plot,
in the approximation of steady state stuff.
so this is
Kilohertz.
kilohertz.
Not hertz.
Sure.
Are there some questions? If not, let's thank the speaker again. So now we'll have a lunch break until 2 p.m. So we have almost 2 hours. Our lunch will happen in this building, in, the place where we went yesterday, opposite was it C3. Opposite was
I want to hear you. So the boundary condition you're setting that the density is constant, and the surface is constant. Yes. So it's that the Lagrangian displacement. Yes, the Lagrangian displacement of density is zero. So the density doesn't change. You are tracking the surface, so it's equivalent to that the Lagrangian displacement of the pressure is zero, which is what is usually. It's equivalent because it's a molecular. It's a quality. Pressure is constant, density is constant. Okay, because I am more used to that, but this is equivalent. Yeah. Yes, it's the same because at the beginning it was no, it's just that so we have this code.
So you can leave your stuff here because someone will be here all the time or it will be locked.
Any style basically. Compare. Because the conditional model you may have the results in the
So if you want to go for lunch, guys follow me.
and it gives you not only
I stopped it already. It's streaming.
Разрешите.
Yeah.